Are there any questions? Yeah?
So it says on the problem that if there are multiple optimal paths that you can list either one. So in that reconstruction of the solution from the cache, if you follow like the first one that appears to be part of the optimal solution, should that at least always lead you to an optimal solution?
Yeah, I mean, basically, I don't want to say too much to solve the problem completely for you, but you're going to be looking at, you're at some spot in the solution, and you can decide whether to go up or down that point. And sometimes it'll be obvious. There'll be a choice, a clear choice. Going up, say, leads to a better solution than going down. But sometimes it won't matter. And in the cases where it doesn't matter, you can pick either one. Okay? Any other questions? Okay. So let's go back to NP-Completeness. First NP-Completeness. This is where I want to be. Okay, this slide pretty much summarizes what we were talking about, where we were last time. We want to prove that a problem Y is NP-complete, meaning we have to show two things. You can't be NP-complete unless you're NP. You have to be an NP problem to be considered NP-complete. The first thing is to prove that Y is a member of NP. And that's usually the easy one. What do you have to do to prove that the problem you're considering is a member of NP? Okay?
Is the polynomial time verified?
Right. You just have to show there's a polynomial time verification algorithm for the problem. Just argue that you can efficiently, if someone gives you an answer to the problem, you can efficiently check it. And that's usually just completely obvious. Next, the other thing, which is usually harder, is you pick a known NP-complete problem, X, and show that X reduces to Y in polynomial time. Okay? The direction is important. I emphasized this last time. You're going from the known NP-complete problem to the candidate NP-complete problem. And the reason that works is, I mean, what you really have to show in step 2 is that every problem for NP reduces to Y. That's a tall order to prove an infinite number of problems reduce to Y. So instead, we take the shortcut. We just show that X, which is known to be NP-complete, reduces to Y. And the reason that works is every problem from NP reduces to X in polynomial time. How do we know that? What is it about X that lets us know that every problem from NP reduces to it in polynomial time? Yeah?
That's the definition of NP-complete.
That's the definition of NP-completeness. Since X is NP-complete, we know that every problem reduces to it. Every problem from NP reduces to it. Okay? So every problem from NP reduces to X. And we've just shown that X reduces to Y. So you compose the reductions. You pick any problem with NP, you first reduce it to X, then reduce it to Y. The composition of those reductions will also be polynomial time. And there you have it. So except for the original NP-complete problem, this is how proof of NP-completeness works. And we got the chicken and egg problem. Where did the first NP-complete problem come from? And we're headed there. We'll do that today. Okay? So, any questions about this recipe here? Why would you want to prove a problem is NP-complete? What good is that? Why bother? Yeah?
It can help you with setting up your algorithm. If you already know it's incomplete, you don't have to try to contrive it.
Okay. So essentially what that was, suppose you're struggling to find a fast algorithm for a problem. Your boss is on your back. You've been working on this a month and you haven't found a fast algorithm yet. What's your problem? Okay? it'd be nice if you could say, oh, look in the book here. It says this problem is NP-complete. That means it's very unlikely, it's unreasonable to expect someone to find a fast algorithm for an NP-complete problem. It's considered very unlikely that any exist. Yeah?
Well, I would say if you know your problem's NP-complete, then you know there's not going to be a better algorithm, so you can take advantage of other algorithms that are already out there for different NP-complete problems.
Yeah, so the fact that a problem is NP-complete doesn't mean you're just going to give up on it. It just means that you're not going to be able to find an algorithm that solves the problem quickly in all cases. And next week we'll be looking at, you know, what do you do when a problem is NP-complete? How do you cope? And there are a variety of strategies. So you could, for example, come up with a fast algorithm that gives you an answer that's close to optimal size. Or come up with an algorithm that works really fast in most cases. And so, it's not like it's the end of the world. But if you know a problem is NP-complete, you do know you're very unlikely to find an algorithm that is polynomial, that's fast in the worst case. Okay, so proofs of NP-completeness. All right, so let's prove. Well, we'll take that problem right there. We want to prove that it's NP-complete. So given a weighted DAG and an integer m, find a path with total weight m in the DAG. Okay? So the first step of the proof is to argue it's a member of NP. So in other words, someone gives you a purported solution. They say, here is a path of length m in this DAG. It's easy to check, right? What would you do? What would it take to check that a path, given a DAG and an m and a path, to check that the path is a solution? Yeah?
Sum up the weights of the path and check it.
Okay. You would first, well, before you sum it up, you'd first check that it really is a path. You know, it'll be a sequence of edges. You make sure every edge is in the DAG, and then it really forms a path through the DAG. And then you would add up the weights and make sure it adds up to m. That's trivial. That's all very easy stuff. So it's easy to find out that, it's easy to argue that this problem up here, this DAG path length problem, is a member of NP. Now, the second step is, we've got to reduce a known NP-complete problem to it. The subset sum problem is a known NP-complete problem. And we already showed how to do such a reduction. Okay? So the fact that the subset sum problem is NP-complete, and the fact that we have previously shown how to reduce a subset sum problem to this DAG problem, proves that the DAG problem is NP-complete. Okay? Okay? Rudrata cycle problem. Okay? Given a graph G, is there a cycle that visits every vertex once before returning to a starting point? Also the Hamiltonian Hamiltonian cycle problem. Okay? Okay, we got to prove that it's a member of NP. Okay? What would be the argument? What would you have to, yeah?
You could just check, first of all, that the path is actually, or that the cycle is actually a cycle in the graph.
Okay.
And then check that each vertex only appears in the cycle once.
Okay. So you're just given a cycle. You got to, you gotta make sure it's legal. All the edges exist in the graph. That it really, each edge follows after the other, and that this thing is a cycle, meaning that it visits every vertex once and ends up where it started at. That's not, that's just a standard kind of graph algorithm. That's easy to verify. All right. Then we have to show a reduction, and we did this one too. We showed that the Rudrata path problem, a known NP-complete problem, reduced to it. All right, we did that last week, I think, or Tuesday. We showed how to take any graph like this and turn the problem of finding a path, a Rudrata path in this, between a pair of vertices, in this graph, into finding a Rudrata cycle in that graph. So we reduce a known NP-complete problem to the candidate NP-complete problem, and that completes the proof. Yeah, so that's a proof we did as well. Right, now here, I want to prove that the independent set problem is NP-complete. So let me remind you what the independent set problem is. You've got a graph, and it has vertices and edges. You are given a goal, a budget, and your goal is, let's say this is the graph and your budget is 5. So the problem is to find 5 vertices in the graph such that no 2 of them are connected by an edge. Right? So if it's a gigantic graph with not many edges, it'd be easy to find 5 vertices that are connected by an edge. If it's a smaller graph with lots of edges, it might be harder. But that's the problem. You're just trying to find 5 vertices such that no 2 of them are connected by an edge. So I want to prove that's NP-complete, and I'm going to do it. I'll just stipulate, we'll just say it's a member of NP. It's easy to verify potential solution. I want to reduce 3-sat to it. So this we haven't done. So remember, 3-sat is the problem of given a Boolean expression in that form. And what that says is not x or y or not z, and x or not y or z, and x or y or z, and not x or not y. So it is written in a stylized form, a bunch of clauses banded together, and each clause is up to 3 variables or their negations or together. And 3-sat problem is to find a way to assign truth values to those variables x, y, and z in this case that makes the whole thing true. Okay? And we could eyeball it and figure out how to assign truth values to x, y, and z. We did that before. But that problem is a famous NP-complete problem. It is almost identical to the problem that was originally proved NP-complete. It is, so we want to prove the independent set problem. So somehow we got to reduce the 3-sat problem to the independent set problem. That is kind of tricky because the problems are so different. How can you take a Boolean expression and somehow reduce it to a graph such that solving the graph problem solves that problem right there? Does anyone have any insight? Yeah.
Well, don't we use a state machine? Or can we use a state machine?
No state machine. We've got to give a reduction.
To represent the Boolean expression, we could represent it as a state machine.
No, the Boolean expression is what it is. We've got to give a way of turning that expression into a graph, together with an n, such that solving the independent set problem solves that problem. Yeah.
I think what he's trying to say is maybe something like making it like almost like a logic gates, where you have a vertice be something with a Boolean expression.
Okay, so
to create a graph to match that.
Okay, so you could say turning that into a bunch of ands, ors, and nots. That you could view that as a graph, right? Is that what you meant? Okay, that's one way to think in terms of turning it into a graph. Let's just think of the vertices of the graph as being your ands, your ors, and your not gates, and then you've got 3 inputs and you wire them together. That's not the direction we're going to go, but that's an approach you could consider.
If we do find a satisfiable answer, then we need at least one true variable in each clause.
One true thing.
One
true disjunct. It could be a variable or its negation.
Right. So one true thing in each clause, and so maybe our independent set has at least one variable from each clause, and so they would have to be connected to prevent.
Okay.
Yeah.
All right. So so that's sort of getting at it. And rather than try to draw in the air, let's just look at a solution. So what I'm going to do is for each conjunct, I'm going to create a little graph like this. So up there we have not x, y, not z, or together. So I'm going to put those literals like that. Okay? Now, suppose we stopped here. What's the largest independent set? What if I ask you to find an independent set of size 2 for this graph? Could you? No, you can't find 2 vertices that are not connected by an edge. So the largest independent set you can find in there is 1. All right, so I'm going to make another one, another one, another one. Okay, so for each conjunct, each thing in parentheses, I'm creating one of these equals here. Okay, what would be the largest independent set you could make out of this?
One of each.
Yeah, you can take one from each. Okay. Now I'm going to add an edge between every variable and its negation down here. So there I've hooked up, you know, this y is hooked up to that not y, and this y is hooked up to that not y, and so on. So every y and y bar is connected. Every z and z bar is connected. Every x and x bar is connected. And now I claim that the graph contains an independent set of size n, if and only if that 3-set instance can be satisfied. Okay. And what is our n? Just think about this. What do we have to set n to be? N is an input to the graph. So when we do the mapping from that thing up there to this thing here, we also need to say what n is.
The number of variables, like x, y.
Okay, so we're saying the number of variables, which would be 3.
The number of variables or the number of variables times 2?
Well, let's see. Let's find an independent set. Let's see what the biggest independent set we can find down here is. Let's just pick,
X, y, z.
let's pick y from right there. So if we pick, what if we pick that y? What does that leave to pick from over here? Right? You can't pick either of these now. If that's in the independent set, none of these can be in the set, and none of the not y's can be in the set. So what could you pick from this triangle? Either x or z. So let's suppose you picked x. Okay? What's left to choose from over here? Well, you could pick x, y, or z, right? So let's say we picked z. What's left to pick from over here?
No, we already picked that, so we have
You already picked y, you already picked x. This y has an edge to there. So you can't pick that because you already picked that y back there.
unpick the x.
And we picked x here, and that x rules that one out. So if we start by picking y, x, z, we're stuck when we get here. Now, do you have any better insight about what n ought to be? How does finding an independent set down here correspond to making that expression up there true? Yeah?
Be 4.
4.
It should be 4. Think of when we pick something, we want to find an independent set of size 4, which means we're going to have to pick something from each of these chunks. Think of it as picking something that is going to be true up there. Think in terms of when you pick a vertex down here, you are saying x bar is true, or equivalently, x is false. So you're picking something here that'll make that first conjunct true. You're picking something from here that'll make the second conjunct true, and so on. And if you can't find a way to pick 4, it doesn't matter what you pick, as long as you can pick something from each of these. If you can't find 4 things that don't have edges between them, you're not going to be able to satisfy that formula. That's the argument. Yeah?
So how about x not y not z?
Okay. So what if we started with not x? Let's pick a different independent set. We pick not x as one. Then over here, what can we pick?
Y not.
We could pick not y. It doesn't have an edge to the x to that there. So we've picked X bar, Y bar. Over here, we can't pick X or Y because they have edges to X bar and Y bar. So you're forced to pick Z. And over here, you can pick either X bar or Y bar. So this, if you pick it that way, there is an independent set size for it. And when we pick X bar, Y bar, Z, it makes that thing up there true. So if there's a solution to that, there'll be a solution like this for n equals 4. 4 is the number of conjuncts. And if there's a solution down here, there'll be a solution up there. That's what we need for the reduction. Right? So someone, thought about this for a long time, had this clever insight about how to do this. And this is typical of a lot of proofs of NP-completeness that go between very different problems. You have to sort of invent some way of mapping one to the other. But this proves that an independent set problem is NP-complete.
Put the word set in that last sentence.
Okay? Now, I realize it can be perplexing on a number of levels. You can be struggling with the definition of NP-completeness. You could be wondering why anyone cares about this. Maybe you don't understand the independent set problem or 3-sat. Maybe the reduction mystifies you. I understand that this is sort of, there's a lot of stuff layered on top here. But I'm willing to help, so are there any questions I could answer? What would help get at it? Yeah?
I was curious about 3-sat. So the whole point of the 3-sat equation is that it'll put it all together and evaluate to true.
The goal, the 3-sat problem is to take an expression like that and find a way to assign true and false to x, y, and z in this case. Assign truth values to the variables such that it makes that thing true. Now, things like this come up in program verification where you're trying to prove a program is correct or hardware is correct. And you can end up with millions of clauses. Thousands or tens of thousands of variables. So this is a problem that folks in industry want to solve all the time. Yeah?
To clarify, so we're starting with 3-sat, and then we want to reduce it to independent set problems.
Right, we're trying to reduce 3-sat to independent set.
So because we solved the 3-sat problem using the independent set problem, it has a reduction.
Well, because the reduction is showing how to convert any instance of the 3-sat problem into an instance of the independent set problem, such that we can solve this problem. If we could solve this problem quickly, we could then take the solution and turn it back into a solution. So, suppose I gave you another instance of 3-sat. How would you turn it into a graph? And what's the rules for turning it into this graph?
Has to be polynomial time.
Well, the goal is to make it polynomial time, but what are the details? What's the details of the conversion algorithm? Yeah?
So for each max term, so that's the x plus y plus z,
Okay, for each thing in parentheses,
you make it a strongly connected component,
you make one of these triangles.
and then
Okay.
you do it for each one. And then for
So you make a triangle for each thing up there, and if it's just 2 elements in it, 2 literals in it, you make one of these. If it's just 1 literal in it, it would just be a lone vertex.
And then for each of the variables, you connect it to its conjugates.
Right. Then you connect everywhere a y appears, you connect it to everywhere a y bar appears. So this y is connected to that y bar and to that y bar. We're making it. Someone else tell me, why do we connect in this independent set? Why do we connect every y to every y bar? What's the purpose of that? Way in the back.
Y and y bar cannot exist in the same
Right.
independent set.
Right. You can't make both y and y bar true. You can think of when something goes into our independent set, we are deciding we want that to be true up there, and we can't make both y and y bar true. So we're preventing you from choosing both y and y bar. And what's the purpose of building these triangles?
Because
Okay.
at least one of them has to be true.
Right. We want to make sure. Okay. Our goal is to make each of these true. So our goal is to find. Down here, our goal is to find 4 independent vertices. We want to make sure that it's possible to find 4 independent vertices, and we want to force there to be 1 in each triangle. So by hooking all the things together, it forces us to find something, 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 something. Have to have an independent set that has a vertex from each of these chunks. When we have a solution to the independent set problem, how do we turn it back into a solution to that? So in other words, we have a solution which is the set containing x bar, y bar, z,
X.
and x bar again. Okay, how do you turn that back into a solution to the...
Just choose the one you picked for the vertices, and those are the ones that are true.
Right. So the vertices that you picked become true. And so since we picked x bar, we're saying x is false up there. Since we picked y bar to be true, we're saying y is false up there. And since we picked z, we say z is true. So the solution that's found here is going to be x is false, y is false, z is true. And that is indeed a solution to that thing up there. Right? So that's kind of a more difficult to understand reduction. But the fundamental thing is you're reducing from the known incomplete problem to the candidate incomplete problem. Okay? Do you think something like this would show up on an exam? No. Someone made their name in the 70s proving something like this. When NP-Completeness was sort of a new idea, there were a few folks that got busy proving things were NP-complete, and they came up with a lot of the proofs you see in your book. That's how they became famous among theoreticians. And no, I'm not going to put that on an exam. But I do expect you to know which direction to do the reduction. Yeah?
Can you give us an easier reduction problem, please?
I'll give you an easy reduction problem for an assignment. But I do not want to grade reductions on it. Especially final exams. Yeah?
So just to be clear with the direction of the reduction, so in this instance, we are trying to reduce, so that right there with all the X at the top, that is the 3-SAT problem.
That's an instance of the 3-SAT problem, known to be NP-complete.
And we're reducing it to the independent set problem.
Because we're interested in proving that it is NP-complete, yes.
Because we already, so in this example, we knew that the independent set problem was NP-complete.
No, the other way around.
Other way.
We're reducing from 3-SAT, which we know to be NP-complete, we reduce to the candidate NP-complete problem.
Okay.
It is no big deal. You can always take some utterly trivial problem and reduce it to an NP-complete problem. You're just saying that if I could solve this really hairy NP-complete problem in fast, I could solve this simple problem fast. That's no big trick. Showing how to find the largest, to find element I in an index by turning it into a 3-SAT problem and solving that wouldn't be very interesting. It's easy to take easy problems to hard problems. What's interesting, what's more challenging is to take a hard problem to another problem. Or the hardest kind of problem to another problem. So the known incomplete problem to the candidate, yeah.
So, because we've shown that this is NP-complete, then in theory we could take some other NP-complete problem and reduce it to the independent set problem as well?
We know, since we have proven that the independent set problem is NP-complete, we know now that there is a way to reduce any problem from NP, including all the other NP-complete problems, to this thing. And also, now that we know this is NP-complete, we can use it in proofs of NP-completeness. Now we can, say there's some other problem we want to prove is NP-complete. We can take this problem, independent set problem, and show how to reduce it to this other candidate problem, and that would prove that's NP-complete. Yeah?
So how do you show all of NP reduces to one of the problems in NP-complete?
Well, we know that every problem from NP reduces to 3-SAT, because 3-SAT's NP-complete.
Yeah, when did we prove that?
Well, we didn't. I'm just asserting it. You're still asking about the original NP-complete problem.
Yeah, like how did the whole of NP?
Okay, well that's where we're headed. We'll look at that. We'll look at it right now. did the first NP-complete problem come from? Because you can't do that proof by reducing from a known NP-complete problem. Now, I've been teaching this a long time, and for a long time I really started, what I did was I took, Stephen Cook in 1970 proved the original NP-complete problem, and the field took off from there. And so the traditional way of teaching this is to take Cook's problem and use that. And that didn't work very well. So a few years ago I just invented another problem. I call it method satisfiability. I think it's easier to understand the proof. So I'm going to show you that first. Now, when I do something like this in a theory class, I always get complaints because people complain, oh, he made up some problem that I can't research on Google. I can't find a YouTube lecture online, other than this one here, where it's talked about. So just be warned, this is just my thing. After we've gone through this, I'll show you the original proof. It'll be easy to understand by that point. But this is just something I dreamed up as a pedagogical solution to teaching this. So we're going to prove that the method satisfiability problem, which I abbreviate MS, is NP-complete. And we're not going to do it by reducing from a known NP-complete problem. So let me explain about the method satisfiability problem. It takes as input a method. All right? So it could be, you can think of it as a method in Java or C# or Python or whatever. You can, if it helps, you can think of it as just, it takes the source code for the method as input. You don't have to be too specific about it. It takes a method as input, and that method, f, that it takes as input, has to be a method that returns a Boolean, and it has to be a method that is guaranteed to run in polynomial time. Okay? So you feed it a method, f of x, and what it will do is it will give you back a value v that will make f of v return true. Or it will report that no such v exists. Okay? So let's look at some examples of how you could use this. If you could implement MS, it'd be really cool. Okay? So suppose you have this method here, is even. Right? It just reports whether or not a function is integer is even. What if you fed is even to MS? What might MS return? It might return 2, because if you feed 2 to is even return true. MS is going to return a value that you can pass to is even to force it to return true. What else might MS of is even return? 0. Any even number, right? 2, 4, 8, 10, negative 8, okay? Okay? So that's what it does. It somehow looks at the code it gets, or it runs the code it gets, or does something with the code it gets, the method it gets, and figures out, somehow, I mean, this would be challenging to implement, and figures out a parameter, it gives you back something you can feed to the original function and so that it will return true. Okay, what about that there? Here is a predicate. Predicate's just a word for a method that returns Boolean. You give it an array, and it tells you whether or not the array sums up to 0. So what happens if you feed that method to MS? Yeah?
An array of just 0?
It could return an array containing 0. What else could it return?
An empty array.
An empty array, sure. Yeah.
-1
-1
and 1.
and 1, yeah, lots of solutions. Here's a couple. It could return an array containing 0. It could return an array containing those. Just any array where the elements sum up to 0. Yeah?
Does the array have to be finite, or does it matter?
Yeah, array has to be finite. Okay? So, let me ask you, what if I gave you your final CADIS assignment was to implement MS? Okay? It seems like a hard thing to implement, right? Right. So you shouldn't be surprised to hear that it's NP-complete. Yeah?
Well, I mean, it depends on how fast
Yeah?
What if the function goes into an infinite loop, like the function you feed it?
The function has to run in polynomial time.
Oh,
The function has to be guaranteed to run in polynomial time. Yeah?
So a deterministic is prime method might not be suitable for the method.
Yeah. Well, think about it. What if you fed this is prime? What would it spit out? It would spit out a prime number. And if you had an is prime method that tested whether the number is prime, and you fed it to this thing, it would spit out a prime number. Now, it might always spit out 2. Or, let's say you had a method that tested whether, maybe your method is 100-digit prime, and you fed it to MS. It would spit out something that makes is 100-digit prime return true, which would have to be 100-digit prime. So if you had this thing, and it ran quickly, that's the cool thing. As he said, you could just have this thing try all possible inputs till it finds one, but that's going to take a long time. The cool thing would be if it ran quickly. You could solve all kinds of problems. Okay? So we're going to prove this is NP-complete. Yeah?
So, does method satisfiability, does this actually exist?
Well,
I mean, for polynomial.
No, well, that is, you know,
It's something, this is theoretical, right?
yeah, it's a thought exercise.
Okay.
Clearly, I can pose the problem. I can say, here's a problem, find an algorithm for it. Yeah?
So what assumptions do you need to make about the language that you write this in for this to be NP? You're assuming Turing complete, what's the assumption there?
Yeah, I'm assuming that that you can express any computation of the language.
Turing complete essentially.
Yeah. And, it depends on what language you're in. If you're in Java, it's a little hard to pass one method as a parameter to another. So maybe we should use C#, where you can do that more easily, or other languages. If you're working in Java, what you're passing in is the source code for the method, instead of the method itself. I'm not going to stress too much about that. Okay, so we're going to prove it's NP-complete, but we're not going to do it by doing a reduction. I can't imagine how you would do a reduction of this anyway. So let's take a break and we'll see what the proof looks like. right, let's get started again. All right, so we're going to prove method satisfiability is NP-complete. All right, so if I ask you to implement, we don't have to implement method satisfiability to prove it's NP-complete. And, you know, how would you go about it? The only way I can think, you know, what I would do if I had to is just try, as he said earlier, just start generating possible inputs systematically till you find one that makes the method you're working on return true. But that could take a very, very, very long time, so it's not going to be a fast implementation. What if you didn't do it that way? What other approach can you think of? Yeah?
Random inputs.
Generate random inputs and hope you know, I guess eventually you'll stumble upon the answer, if there is one. The problem is, you'll never know if it's impossible to satisfy the method, yeah?
You could feed it non-infamously and like an infinite number of threads, and then each one of them checks for
Yeah, sure, you could do multi-threading and have them check independently for ones. But the other thing you could do, I mean, how would you do it? Suppose I said, hey, give me a value that makes this return true. Yeah?
Do we guys see the internals of
Yeah, let's say you can see the internals.
maybe
Yeah,
like parse inside of it and then try
yeah, you could start looking at the code and taking it apart. You know, suppose that method was called F instead of is even. It wouldn't be too hard for you to look and say, yeah, you know, in fact, any even number will make this return true. You could analyze the code. You could have a program do that as well. But as programs get more and more convoluted, it gets harder and harder to do. But it's something you can think about. Now, to prove it's NP-complete, we've got to prove method satisfiability is a member of NP. What does that mean? What do we have to show to argue that method satisfiability is a member of NP? Yeah?
Our verification algorithm for MS is just the function that we fed it, right? So
Okay.
we would feed our output back into F, and
Right.
then if it returns true, then MS gave us a value.
Exactly. So you said it exactly right. Suppose someone says, you know, someone just asserts that 8 is a solution for MS it is even. Right? How would we verify that 8 is a correct answer for this method call?
You feed it to F or is even.
Right. You just feed 8 to is even and see if it does return true. All you're saying when you return 8 is you're saying 8 will make is even return true. So you just take the answer that someone gives you, and to verify it, you just feed it into that method right there. Now, that's not enough though. What else do we have to show besides showing that there is a verification algorithm? What's the restriction on this verification algorithm? Yeah?
That it runs in polynomial
It
time.
has to run in polynomial time. How do we show that?
Well, that was one of the constraints on F.
Right.
So F has to run in polynomial time.
Right. We said up front that MS only works on the method that you give as input to MS has to run in polynomial time. Otherwise, all bets are off. So obviously, then our verification algorithm, that constraint is there to make sure the verification algorithm will work in polynomial time. Okay. Good. And this is just more examples. So it's easy to verify. If someone stumbles on an answer, it's easy to verify. Now what have we got to show? Yeah?
That all problems in NP can be reduced to it.
We got to show that every single problem from NP reduces to this problem. In other words, we got to show how to solve. You take any problem out there that's a member of NP, show how to solve it. Here, yeah.
Isn't NP at this point empty?
No. NP complete. You know, if this is 1970, we haven't proven any problems are NP complete yet. But NP is a set of all problems that can be verified in polynomial time. So it exists. So we got to show that they all reduce the method satisfiability. Okay. Okay, so let's think about this. Let's think about the subset sum problem, for example. And we'll let V sub SS be the verification algorithm for the subset sum problem. Okay? And, you know, and of course, V sub SS runs in polynomial time because otherwise it wouldn't be a verification algorithm. Yeah?
Subset sum problem is just where you have an integer and you want to prove that a bunch, a
subset adds up to that.
Right. You want to find, you're given a set and an integer, and you want to, a set of integers and an integer, and you want to find a subset of the set that adds up to the integer. So it'll have a verification algorithm. We'll call it V sub SS. So for example, V sub SS, this is the yellow right there is the input, the problem instance for the subset sum problem. The red is claimed to be a solution. And the verification algorithm would just say true, yeah. This is a subset of that and it adds up to 8. Okay? It was, if you gave it this instance and this solution, it would say no, that's not a solution. The set 1, 9 doesn't add up to 4. Okay, so we're working with the verification algorithm. Okay? Let V of 3 set be the verification algorithm for 3 set. So it takes this as input and this proposed solution and says no. This assignment of truth value does not make that thing true. Or it says that this assignment makes that true. So verification algorithms. Okay, how would you describe that method right there? What does F1 do? Yeah?
It just calls via SS and checks whether or not that's going to be.
Yeah. So F1 has that yellow problem instance baked into it. So it just takes a proposed solution to that yellow thing and reports whether or not it is a solution. Okay? So you provide the proposed solution. It'll check to see if it is a solution to that particular problem instance. Okay? So it's a Boolean valued function that tells you whether or not V is a solution to the instance highlighted in yellow. So that's what F1 does. Does anyone see where we're headed yet?
Well, this can encapsulate any method.
Okay. Well, yeah.
F1 is what you would need to pass the method satisfiability.
Yeah.
And this is a polynomial conversion.
Yeah. What happens if you pass F1 to MS? What's MS going to return if you give it F1 as input?
A V that satisfies.
It's going to give you back a V, such that if you pass V to F1, you get true back. What's another way of saying what it does?
Finds a solution to the subset sum problem.
Yeah, it finds a solution to that yellow instance of the subset sum problem. Right? I'll back up and come back to that. So if you feed F1 the set 1, 2, 5, it should return true, right? Because 1, 2, 5 is a subset of 1, 2, 5, 9, and 1, 2, 5 adds up to 8, which is the goal. Okay? How would you describe that method right there? Yeah?
The report that there's no solution?
Well, but what are we asking when we call this when we do this? Yeah.
I think we're, V is a proposed solution for the 3-step problem.
For this instance of the 3-step problem.
For this is, okay, yeah, for that instance. We're seeing if it is actually a solution.
All right, so we're just checking to see if this parameter is a solution to that. And in fact, there is a solution. We make X and Y both true. That would work. Okay? So what's the difference between this and just the verification algorithm for 3-set? What's the distinction? How does F2 differ from the verification algorithm for 3-set? Yeah?
F encapsulates the problem.
The instance. Right, so what he said was F2 encapsulates the instance. In other words, 3-set, the verification algorithm for 3-set takes an instance and a solution and reports whether the solution is really a solution. F2 just takes a proposed solution. It already has the instance built into it. It just reports whether V is a solution to this thing that's built into the method. So it's more specialized. This is a verification algorithm just for this instance. All right? Okay, so here's our first one, the F1, that works with the subset sum problem. And what would be returned if we passed F1 to MS? What's MS's job when we pass this thing? Yeah?
The yellow part.
No, it doesn't return the yellow part. Yeah?
Return a solution.
Right, it returns a solution to the yellow part. Holy cow. What does this mean? Well, look at another one. So it would return a solution to the subset sum instance. So what if we had a set and a goal, and we wanted to find a subset? We wanted to solve the subset sum problem for a particular set and an integer. How could we trick MS into solving it for us? Yeah?
Bake in the instance and then feed the function into MS.
Yeah. We would just replace that yellow instance with any instance we please. And feed this thing to, feed the new F1 to MS. And it's either going to, what's MS going to do?
Find the answer. Or find something better.
It's going to return something that makes F1 return true, which, or tell you that there is no such thing, and that is, so it's going to, we can force MS to solve anything we want to. Okay? Same thing with 3-SAT here. We can take any 3-SAT instance, plug it in there, and MS of F2 is going to return something that satisfies it if it exists. Well, in this case, it'll tell us that there is no solution. So MS is either going to find a solution or tell us it none exists. Okay, all right, so how does this really help our proof that MS is NP-complete?
Because if MS wasn't NP-complete, it would be saying that you found a polynomial time algorithm to solve NP problems.
Well, we don't want to start by assuming it's not NP-complete. We're doing a more constructive proof. How can we argue now that you take any problem from NP, you can reduce it to method satisfiability in polynomial time? Yeah?
I argue that the simple F here is a reduction from...
Okay, so yes, so the reduction is, take the verification algorithm, the reduction is to build this method here. So if we want to solve the Hamiltonian cycle problem, we implement the verification algorithm for Hamiltonian cycle. We stick the instance of the Hamiltonian cycle problem we want to solve right there. And then we feed this function to MS. It will return something that makes this verification algorithm return true if something exists like that. Or it'll return null or whatever otherwise. Solve the problem. We can reduce any problem. It's very quick to build this thing right here. Do you have a question?
I was just going to say, so we know we can do this, we can convert it to an instance because for NP, everything in NP by definition has a verification in polynomial.
Yes.
Right?
Right.
Okay.
Now, is it so? So what we're exploiting here is the fact that every problem from NP has a polynomial time verification algorithm. That's what makes this a polynomial time. Well, that's what lets us argue that this problem is a member of NP. Should it be surprising that we're exploiting the fact that every problem from NP has a polynomial time verification algorithm? Why not? Why is that not surprising? It's kind of a strange question. Yeah.
That's one way to prove that this solves all those problems?
Yeah, that's one way, but you could almost say it's the only way. Because the only thing that every problem from NP has in common is that they all have a polynomial time verification algorithm. So of course we have to leverage that. That's the only thing they have in common. So to be clear, you pick any problem from NP. It can be a simple problem, it can be a complicated problem. You just build this method where a call to the verification algorithm goes there. The instance goes here. There's your method. It's really quick to build. You pass it off to MS and it will solve the problem. You've tricked it into solving the problem for you. So why don't we solve all the problems from NP this way?
Yeah, where's our long-term security?
Yeah?
Well, I mean, like, if you're trying to find solutions, you have to feed it as many as you're going to try and check, so.
Sure, but we could, you got to solve a problem. You build this method in, in a millisecond. Pass it to MS. Yeah?
Because didn't we guarantee with MS that the function had to be run in polynomial time?
The verification algorithm has to run in polynomial time. Yeah. Not
Not the function itself.
right. Well, yeah. We have to guarantee that. Yeah, you're right. We have to. This has to, for MS to work. This has to run in polynomial time. Does it run in polynomial time?
Found it.
Make it louder instead. Okay. So, okay, she makes an important point. We require, the only thing you can pass to MS, I'm requiring it, has to be something that runs in polynomial time. Does this run in polynomial time? Yeah. If you call this thing, all it does is call V. And we know V sub 3 set runs in polynomial time because it's a verification algorithm, and they all run in polynomial time. So why don't we solve all the world's problems this way? Just, yeah.
MS could spin forever and not find a solution because there is no solution.
Well, yeah, MS's job is to, the specification is you give it something and it either finds a solution or tells you that it exists. Yeah.
So, I mean, if it is NP complete, then it will probably run in NP complete time.
Well,
And so it will take too long.
yeah. The bottom line is, yeah, we don't do it this way because where's the implementation of MS? We don't have a fast implementation of MS.
Could we also feed MS with an instance of MS? Since MS is an NP, so then we can put that into MS.
True. Yes.
Yeah.
Well, we don't need to go there. So, yeah, if someone, tonight came up with a really fast polynomial time, running time implementation of MS, then we could solve any problem from NP quickly by reducing it this way to MS. But if we found that fast algorithm, that would prove P equals NP. We would have found a fast algorithm for an NP complete problem. So to prove something's NP complete, you don't have to, we have to prove that there's a polynomial, that a solution produced by MS can be verified quickly, and we dealt with that. We don't have to prove MS itself can run quickly. We don't know that. But what I've shown you is, you pick any old problem you want from NP, you can easily cast it into a problem for MS. Yeah.
So the next step is, we have to show like 3-set reduces to that.
No, there is no next step.
Oh.
This finishes the proof. MS is NP complete.
It's our seed, right?
Yeah, this is our original NP complete problem. It's not Cook's, it's mine. Okay? Yeah.
So any problem that makes NP equal to P would be like the original NP complete problem?
I don't follow the question.
Like this problem, if you solve this problem,
Mm-hmm.
then NP would equal P.
Yeah, if you found a fast algorithm for MS, that would prove P equals NP. But that's true of any NP complete problem. If you solve any NP complete problem quickly, you prove P equals NP. All right. So, method satisfiability is NP complete. Okay, and this just summarizes it. This is what we've been saying. Okay? Now, let's pretend it's 1970. And we as a class have just defined the notion of NP completeness and proven that the method satisfiability problem is NP-complete. What's next on our list of things to do? We have this suspicion there are other NP-complete problems out there. We doubt this is the only one. What do we do the next day?
Start finding other ones.
Yeah, start finding other ones. And that's what they did. As soon as they proved the original NP-complete problem, they started trying to find other ones. Okay, what will it take? This is our starting point. What do we have to do? Yeah?
Start with method satisfiability and reduce it to other forms.
We got to reduce method satisfiability to something. Maybe the Hamiltonian cycle problem. Maybe we reduce it to the independent set problem, whatever. We're going to have to define a reduction from method satisfiability to some other problem to get off the ground. Otherwise, this is a dead end. And I argue that I don't see how you would do it, method satisfiability. Okay? I think if this had been the original NP-complete problem, they would have had to go find a different one because it's hard to see. Well, I haven't thought about it that hard, but we'd have to find some way to relate this to these other famous problems. Okay? Fortunately, Cook didn't have that problem. So the original NP-complete problem was circuit satisfiability, not method satisfiability. It was circuit satisfiability. And basically, what he said is you're given a circuit, a Boolean circuit, a logic circuit, a combinatorial circuit, meaning it doesn't have flip-flops or feedback. It's just a DAG with vertices or logic gates. You can think of this ands, ors, and nots. And the problem is, you put bits in, you got inputs coming in at the top, and you got a single input coming out, the output coming out the bottom. They're passing through all these logic gates. And the challenge is, find a way to set the wires to zeros and ones, such that one comes out the bottom. What problem does that sound a lot like? That's a lot like 3-sat. 3-sat and this problem are equivalent. Okay, so that was his original problem. And I'm just going to sketch the proof here in a few minutes. It's not a difficult proof. If you really wanted to be formal about it, there are a lot of details. So think of the simplest model of a computer you could think of. You don't want to think about a modern microprocessor with all kinds of multiple cores and pipelined architecture, not any of that. Just the simplest plotting architecture from 1950 will do, because you can compute anything on there if you wait long enough. And the way you can think of it works is, it works in phases. You've got a memory, you've got registers, you've got an instruction register, a program counter. So you've got some state, and then you've got some logic. And the way a computer works is, the memory has some values in it. And then every clock cycle, the stuff filters from the state through this circuit here. And then something is stored back into the state. And then another clock cycle. Stuff comes out of the state, goes into the circuitry, and something gets stored back in the memory. And it just runs like that. Now, what you could do is, instead of building a computer that way, with a clock, just build it this way, with a whole pile of hardware. So instead of reusing your circuitry every clock cycle, just make a copy for every clock cycle you need. So the first clock cycle, the signal will be down to here, and the next clock cycle, it makes it down to here. And so if your program is going to run in a second, and if it has to run for 1 billion clock cycles, you're going to need 1 billion layers of this. But in principle, it's possible, right? So what he argued was, you can take any program that runs on a computer, and you could turn it, you could run it on a massive circuit. Okay? And then he said, so this is how it works. You got some memory, you get feeds in there, feeds in there, feeds in there. You could eliminate the memory, just replace it with wires that lead directly from one stage to the next, because you really don't need memory now. Memory is just there to produce input for the next stage. So now you really do just have a massive combinatorial circuit. Okay, I'm just go straight to this picture. So take the problem you want to solve. It has a verification algorithm. Do what I just said and build a massive circuit to compute that verification algorithm. Now, the depth of this is limited by the complexity of the verification algorithm. The verification algorithm runs in polynomial time. So this is only going to be polynomial deep. On those wires, you feed in a description of the problem instance you want to solve. Remember, this is sort of a hardwired implementation of the verification algorithm. You feed the problem instance up there, so you wire all these to ones and zeros. You leave those unbound. That's where the proposed solution would go in. Then you feed this to circuit satisfiability. Somewhere at the bottom there's a bit that we're looking at. That's the output of the algorithm. So, what will circuit satisfiability do? What's its job? Yeah?
Loop through this with every combination of...
Well, no, what's the job? Circuit satisfiability. You give it a circuit with some inputs that aren't specified. What's it do?
It sees if it's a solution.
It tries to find a way to put trues and falses on those inputs so that a true comes out the bottom. In other words, it finds an input that makes the verification algorithm return true. So it's analogous to the method satisfiability problem. But the cool thing is, once you've proven this is NP-complete, now, and you observe that circuit satisfiability is the same as 3-SAT. You can convert one to the other. Then you can take 3-SAT and start doing reductions like we did today. Right? We reduced 3-SAT to independent set problem. So Cook's original problem was easier to work from than mine. Anyway, let's end there.